All right, folks, finishing off the chapter, we're going to take a look at what's called improper integrals. Now, I think the topic and concept in this section is pretty cool. It's a little trippy, if you will, mainly because infinity is involved. This material will lay the foundation for our future work with infinite series, and that future is the next couple of chapters that we look at. And here's where it comes from. You know, way back when we defined a definite integral, there were two requirements that we really didn't have to worry about. Well, and we have to worry about them now. Those two requirements, well, let's take a look at what they were. The definite integral, the integral from a to b, f of x dx, it really has the following two requirements. Requirement 1, the interval a to b was a finite interval. Requirement number 2 was that using the fundamental theorem of calculus requires our integrand, f of x, well, it has to be continuous and bounded on closed interval ab. Folks, any integral that violates number 1 or number 2 is called an improper integral. So for example, the integral from 1 to infinity, 1 over x squared dx, or the integral from negative infinity to infinity, 4 over x squared plus 2 dx, those integrals violate number 1. You know, we're not on an interval, we're not integrating on an interval that is finite. On the other hand, the integral from negative 1 to 1 of 1 over x squared dx, well, that integral violates number 2. And it violates number 2 because on the closed interval negative 1 to 1, the integrand, 1 over x squared, is not continuous at x equals 0. So it's a discontinuity at x equals 0. In fact, that's a discontinuity that we're going to call an infinite discontinuity. All right, so a natural question that you may have is, how do we attack an improper integral like this? The integral from 1 to infinity, 1 over x squared dx. And quite simply, the answer is, we're going to do a simpler but yet related integral. And in order to see what I mean by that, let's head to the chalkboard. All right, so hey, the question we have right now that we're trying to analyze, we're trying to figure out, is how in the world do we attack the improper integral from 1 to infinity, 1 over x squared dx? You know, how do we do that? Keep in mind that that improper integral would match up with the area of a region that's unbounded. So it's the area under the curve 1 over x squared above the x-axis from 1 to infinity. It's an unbounded region. So what we're going to do is we're going to do an easier problem. For example, we could easily do the integral from 1 to 2, 1 over x squared dx. I mean, that would just be, you know, this area. We can easily do that. We can get an antiderivative for 1 over x squared. The antiderivative for 1 over x squared is negative 1 over x. We could evaluate that from 1 to 2 using the fundamental theorem of calculus. So it's negative 1/2 plus 1. We could get the area to be 1/2. That was an easier problem to do. And we could integrate from 1 to 10, 1 over x squared dx. So you come out here to 10. You can find that area. You can do that. That's an easier problem. You still get the same antiderivative. And so you'd have negative 1/10 plus 1. So you get 9/10. So those are easier problems. So why don't we do another easier problem? But generalize what we're doing here. Why don't we just, instead of integrating from 1 to 2 or 1 to 10, let's just pick some arbitrary value b. Let's just integrate from 1 to b. We can do that. I mean, we can integrate from 1 to b, 1 over x squared dx. We know the antiderivative of 1 over x squared. That's negative 1 over x. Evaluate that from 1 to b, so you get negative 1 over b minus a negative 1. Or you know what, I could think of that as being 1 minus 1 over b. So we've generalized to any upper limit of integration b that's greater than 1. And notice we kind of came up with a little formula. Notice this little formula. If b is 2, I can put 2 in here for the b and get 1/2, which we already have here. If b were 10, I could use this little formula. 1 minus 1/10 is 9/10. So we have a little formula here. When we generalized to just integrating from 1 to any value b, we came up with a little formula. So how does that help us? How does that help us do this? Integrate from 1 to infinity. 1 over x squared dx. Well, what we're going to do now is we're now going to let b head off to infinity. So we have our little formula. Let's let b head off to infinity. And see, the limit as b goes to infinity of 1 is 1. The limit as b goes to infinity of 1 over b is 0. So this limit is 1. That's the actual area of that unbounded region. And you know, here's what we did. We looked at this. It's an improper integral. And we kind of said, improper integral, we can't do it. But what we can do is we can do an easier problem. We can integrate from 1 to b, 1 over x squared dx. And then after we do that, we take the limit as b goes to infinity. So we kind of did two things here. And this is exactly how we are going to attack these types of improper integrals. And I know at first glance you're thinking, well, this unbounded region, if the region is unbounded, if this improper integral represents an unbounded region, a region that goes on forever and ever, the area would be infinity. And that's not the case here. That's why this stuff is kind of trippy. It's 1. We just determined this is 1. And it may go against your intuition that a region that is unbounded has a finite area. And that's because infinity is involved, folks. So when infinity gets involved, sometimes our intuition breaks down and we have to rely on the mathematics. So what we're going to do now is I want to formalize what we just kind of discovered here. So let's head back to the slides and formalize all of this in a definition. All right, so our work at the chalkboard does give rise to the following definition. I'm going to break this into 3 parts. Part 1, if your function is continuous on the interval a to infinity, then the integral from a to infinity f of x dx needs to be rewritten as the limit as b goes to infinity of the integral a to b f of x dx. So in short, the improper integral a to infinity f of x dx, you can't do it. Instead, you integrate from a to b f of x dx, and then out front of that, you put the limit as b goes to infinity. Part 2, if your function is continuous on the interval negative infinity to b, then the integral from negative infinity to b f of x dx, that equals the limit as a approaches negative infinity of the integral a to b f of x dx. And then part 3, if f is continuous on the real numbers from negative infinity to infinity, then the integral from negative infinity to infinity f of x dx, well, that's equal to the integral from negative infinity to c of f of x dx plus the integral from c to infinity f of x dx. So we're kind of using the old interval addition property there. We're finding a convenient value, a convenient real number c, to break up the integration and use the interval addition property. Now, folks, we're introducing some vocabulary here. If the limit exists, we are going to say the improper integral converges. If the limit doesn't exist, we say the improper integral diverges. In number 3, if either integral on the right diverges, then the original improper integral from negative infinity to infinity, it diverges. All right, so I think it's time, let's do an example. So here we have 4 parts. In part A, we're going to integrate from 2 to infinity, 1 over x squared dx. In part B, we're going to integrate from 1 to infinity, 1 over x dx. Part C, we're going to integrate from 0 to infinity, cosine x dx. And then part D, we'll integrate from 0 to infinity, 1 over 1 plus x squared dx. So you know the drill. Have these written down because, I'm heading off to the chalkboard to work through them. Okay, this example had 4 parts, 4 improper integrals that we're going to evaluate. A was the integral 2 to infinity of 1 over x squared dx. And I put B, C, and D over there. I'm only going to be able to do them one at a time here. So let me pull A on over. 2 to infinity, 1 over x squared dx. For this one, I'll do a quick picture. It looks like the first example we just, we looked at, except this time, it's the area of that unbounded region. We know it's an improper integral. We can't do it. We immediately just rewrite it as the limit as b goes to infinity, the integral from 2 to b, 1 over x squared dx. So we get our antiderivative for 1 over x squared. We know that's a negative 1 over x. Evaluate it from 2 to b. And when we evaluate that from 2 to b, we get, a negative 1 over b minus a negative 1/2, so that's a plus 1/2. Now we do the limit. The limit as b goes to infinity of negative 1 over b, that is 0. The limit as b goes to infinity of 1/2 is 1/2. So we ended up with a finite positive number. So the vocabulary. This tells us that our original improper integral, it converges, and it actually has a value of 1/2. All right, part B, I'm going to erase this. So part B is integrate from 1 to infinity a 1 over x dx. All right, well, let me put a quick picture up for this one. It looks something like this. That's the graph of 1 over x. So it's that unbounded region. But it's an improper integral. Can't do it, but I know to rewrite it as the limit as b goes to infinity, the integral 1 to b, 1 over x, dx. Okay, now I get my antiderivative. We know the antiderivative of 1 over x is ln absolute value of x. Evaluate it from 1 to b. Use my fundamental theorem of calculus, which gives us the natural log of b. I can get rid of the absolute values because we're talking about positive numbers here. 1 to infinity minus the natural log of 1. Well, that's the natural log of 1, that's 0. So we're just left with evaluating the limit as b goes to infinity, natural log of b. So let's see, natural log. I kind of know the graph of natural log. I mean, it does something like this. So as b goes to infinity, this limit is infinity. That means the area of this unbounded region below the graph of 1 over x, above the x-axis, from 1 to infinity, that unbounded region, it has an unbounded area. It has an infinite area. Vocabulary, because we got infinity here, we would say that the improper integral from 1 to infinity, 1 over x dx, we would say that improper integral diverges. The limit wasn't approaching a nice real number. All right, part C. You know, I kind of have a gut feeling without doing any work whatsoever that C is going to diverge. And the reason why I'm saying that is because the graph of cosine x, you know, we know the graph of cosine x is a wave. It just keeps bouncing back and forth between -1 and 1 forever and ever. But let's go through the mechanics. It's an improper integral. We know to rewrite that as the limit as b goes to infinity, the integral 0 to b, cosine x dx. The antiderivative of cosine, we know that is sine. Fundamental theorem of calculus, see, gives us the sine of b minus the sine of 0. Sine of 0 is 0. The limit as b goes to infinity of sine. Well, sine is a wave. It keeps bouncing between 1 and -1, 1 and -1. As you head out to infinity, it keeps bouncing between 1 and -1. It's not approaching a single value, a single number. It oscillates. This limit does not exist. It oscillates. Because the limit doesn't exist, because it oscillates, that tells me my hunch was correct, that improper integral diverges. All right, let's do part D. Part D. Integrate from 0 to infinity. One over 1 plus x squared dx. I know I have to rewrite this as the limit as b goes to infinity. Integral 0 to b. 1 over 1 plus x squared dx. And this is a very, very friendly integral. The antiderivative of 1 over 1 plus x squared is inverse tangent. And the limit as b goes to infinity. We use our fundamental theorem of calculus. Inverse tangent of b minus inverse tangent of 0. Well, inverse tangent of 0 is 0. So we just have to compute the limit as b goes to infinity, inverse tangent of b. If you suffered through my Calculus 1, when we started to talk about the inverse trig functions and the derivatives of the inverse trig functions and integrals that gave rise to inverse trig functions, I spent quite a while reviewing the inverse trig functions, and there was one inverse trig function I said you needed to remember the graph of. It was inverse tangent. I said it would be important throughout the rest of your time in calculus, and it is, and here's why. This is the graph of inverse tangent x. As you head to infinity, pi over 2 is a horizontal asymptote. So as you head to infinity, the limit is pi over 2. So as b heads to infinity, this limit is pi over 2, which tells us that our original improper integral, it converges, and it has a value of pi over 2. I want you to practice a couple of them here. So let me write down the ones I'd like you to do. 21 and 23, so you know the drill. Pause the video, go to the exercises, do numbers 21 and 23, then restart the video, and I'll be here at the board working through them. Hey folks, number 21, you were asked to integrate from 2 to infinity, cosine of pi over x, and then all of that over x squared dx. Alright, so here's what the first thing you should have done is say, I have an improper integral, I can't do it, so I need to do the limit as b goes to infinity, the integral from 2 to b, cosine of pi over x, and I'm going to rewrite that as pi x to the negative 1 over x squared dx. So now we need to come up with an antiderivative for the cosine pi x to the negative 1 all over x squared. I'm actually going to take this integral and I'm going to pull it off to the side over here and just kind of work with coming up with an antiderivative. Alright, so hopefully you realize this is a basic u substitution. U is pi x to the negative first, du is negative pi x to the negative second dx, or du is a negative pi over x squared dx, or negative 1 over pi du is 1 over x squared dx. So when I substitute in the cosine of u and the 1 over x squared dx, well, that's negative 1 over pi du. So I'll rip the negative 1 over pi out front, get my antiderivative, which is just sine of u, resubstitute, resubstitute with the correct trig function written down, and I now have an antiderivative for this mess. So let me pull that over here, my antiderivative. So I have the limit as b goes to infinity. Antiderivative is negative 1 over pi sine, I'm going to write that back as pi over x instead of pi x to the negative first. And I have to evaluate that from 2 to b. So, fundamental theorem of calculus time. So b comes in for the x, so I have a negative 1 over pi sine pi over b minus negative 1 over pi, so I'll make that plus 1 over pi sine pi over 2. Alright, So I'm going to look at these. There's an old property law of limits. The limit of a sum can be rewritten as the sum of two limits. I'm just going to do them, individually for this one because I think I can. In other words, I think I can determine what the limit as b goes to infinity of negative 1 over pi sine pi over b. I think I can do that limit just by talking about it because as b goes to infinity, well, that's a constant, pi over b. So as b gets incredibly large, pi divided by an incredibly large number is heading to 0. The sign of 0 is 0. So negative 1 over pi times 0 is 0. So the limit as b goes to infinity of this first term is 0. All right. Sine of pi over 2, that's 1. So 1 over pi times 1 is 1 over pi. It's a constant, 1 over pi. So the limit as b goes to infinity of 1 over pi, the limit of a constant is that constant. So for number 21, you should have concluded that this improper integral, because we have a real number here, converges, and its value was 1 over pi. All right, hey, I asked you to do another one, number 23. So let me erase the board. I'll be right back, and we'll do number 23. All right, here at number 23, you're asked to integrate from 0 to infinity, e to the u over e to the 2u plus 1. Improper integral, can't do it, so I rewrite it as the limit as b goes to infinity. The integral from 0 to b, e to the u over, now this e to the 2u, I'm going to rewrite that as e to the u squared. Because, now let me just pull the integral over here. When I do this rewriting, e to the 2u as e to the u quantity squared, I kind of see if I do a substitution, if I let w equal e to the u, then dw is equal to e to the u du. So when I substitute in, I see my denominator is a u squared plus 1, and the e to the u du is just dw. Sorry, that should be a w squared plus 1. So when I substitute that w in for e to the u, dw is e to the u du, inverse tangent. This is inverse tangent looking at us. So we have inverse tangent of w, resubstitute, that's inverse tangent of e to the u. That wasn't too bad. So I pull that over here. I know what this says. So limit as b goes to infinity. I have inverse tangent of e to the u. Limits of integration are 0 to b. So I get, well, let me write down this. Limit as b goes to infinity. Inverse tangent of e to the b. Inverse tangent of e to the b minus inverse tangent of e to the 0. When 0 comes in, I have e to the 0. E to the 0 is 1. So it's inverse tangent of 1. That's kind of nice. All right, so what is the limit as b goes to infinity of inverse tangent e to the b? Well, we know as b goes to infinity, e to the b is getting incredibly large. Inverse tangent, that's a graph that we should know. We know inverse tangent does this. It has a horizontal asymptote at pi over 2 and one at negative pi over 2. But as you head to infinity, this limit is pi over 2. Okay, inverse tangent of 1. See, inverse tangent of 1 is pi over 4, which is a constant. The limit as b goes to infinity of pi over 4. The limit of a constant is that constant. So pi over 2 minus pi over 4 is pi over 4. That tells me that this improper integral converges, and its value is pi over 4. Yeah, that was a good one. So let's head back to the slides and see what is next. All right, as we saw in that first example, we still need to remember techniques of integration. And, part D, we had inverse tangent involved in the antiderivative. And knowing the graph of inverse tangent helped us tremendously in doing the limit. I asked you to do 21 and 23. So in 21, you saw, good old-fashioned, basic U substitution. Then in 23, we saw substitution and then an inverse tangent. So the next thing we're going to do is another example. We're going to integrate from 2 to infinity the quantity 2 minus x e to the negative x dx. So get this in your notes because I'm heading off to the chalkboard to work through it. All right, this example, we're going to integrate from 2 to infinity the quantity 2 minus x e to the negative x dx. First thing we do, rewrite it. Limit as b goes to infinity. The integral from 2 to b, 2 minus x e to the negative x dx. So now I need to figure out this antiderivative. So as always, let me bring it over here. Alright, so we may be tempted to say, well, let's distribute that e to the negative x, but I'm just kind of looking ahead. If I distribute this e to the negative x, I can quickly and easily integrate 2e to the negative x. But this minus x e to the negative x, well, sounds like that would require an integration by parts. So I'm just going to start off using integration by parts. I'm going to let u equal 2 minus x, dv equal e to the negative x dx. So we get du is just the negative dx, and v is negative e to the negative x. So when I take my original integral and I crank it through integration by parts, I get u times v. So negative e to the negative x times the 2 minus x minus the integral of v du. So that's a negative e to the negative x, negative dx. Negative times negative is positive. So I get negative e to the negative x, 2 minus x. The antiderivative of e to the negative x is just negative e to the negative x. So minus a negative gives a plus e to the negative x. So I have an antiderivative. Let me pull the antiderivative back over here. And see, negative e to the negative x, 2 minus x, plus e to the negative x. And we need to evaluate that from 2 to b. All right, so let's see. The b goes in first. So we have negative e to the negative b times 2 minus b plus e to the negative b minus. Okay, now the 2 goes in. Oh, notice right away when the 2 goes in, 2 minus 2 is 0, so that term will be gone. Well, that's nice. But we still have this e to the negative second. Let me get rid of negative exponents, because I see a problem right here in doing this limit. So there's an issue there. So if I get rid of the negative exponents, that might shed a little light on things. So, so this would be what? The opposite of 2 minus b over e to the positive b. This is 1 over e to the b, and this is just a 1 over e squared. Okay, I'm not so concerned here about these last two terms. The limit as b goes to infinity of 1 over e to the b. The denominator is getting incredibly large. That limit is 0. This is a constant. So the limit as b goes to infinity of the constant 1 over e squared is going to be 1 over e squared. It's this term right here. The limit as b goes to infinity. The numerator is going to infinity and the denominator is going to infinity. So the numerator and denominator are both going towards infinity. Infinity over infinity. That's an indeterminate form that would require L'Hopital's rule. Yeah, we need to remember L'Hopital's rule. We haven't dealt with that in a while. So let me erase this work that we've already done, and let's review L'Hopital's rule. So it's this is what I'm trying to analyze. Or if you prefer, you could see this as the limit as b goes to infinity of negative 2 plus b over e to the b. Infinity over infinity. So you remember L'Hopital's rule, which if you suffered through Calc 1 with me, I always indicate I'm now using L'Hopital's rule by making an equal sign and above the equal sign writing an L with the circle in it. That's my signal that I'm using L'Hopital's rule, the hospital rule. So if you remember, it's do the derivative of the numerator over the derivative of the denominator. Then substitution would give us 0. So we had to use L'Hopital's rule to do this one. Gives us 0. We said that one was 0. We already said the limit as b goes to infinity of the constant is the constant. So the limit is negative 1 over e squared, which tells us the original integral converges, and it has a value of negative 1 over e squared. So I really liked this one because, you know, it's an improper integral, easy to rewrite it, but we needed to remember integration by parts, and then we got to review another old topic, L'Hopital's rule. So yeah, that was a fun one. All right, here's the one I want you to do right now. So pause the video, go into the exercises, do number 31. After you've done 31, restart the video. I'll be here at the board working through it. All right, folks, at 31, you're asked to integrate from 1 to infinity, 1 over v times the quantity v plus 1 dv. Improper integral, so you immediately start by rewriting this as the limit as b goes to infinity, integral 1 to b of 1 over v times v plus 1 dv. I don't know about you, but I'm kind of smiling right now. This is absolutely positively already set up for us to do the technique of partial fraction decomposition. It's so friendly. 1 over v times v plus 1 equals an a over v plus a b over v plus 1. Multiply both sides by the LCD. Pick convenient values for v, so I would let v equal 0 and immediately get, let's see, 0. A is equal to 1. And v equals negative 1. And I immediately get what, negative, or 1 equals negative b. B is negative 1. So our integral of 1 over v plus 1 dv, we're going to write that as a over v. So it's a 1 over v minus 1 over v plus 1 dv. Pretty friendly. The natural log absolute value of v minus the natural log absolute value of v plus 1. So I have an antiderivative. So let me bring the antiderivative back over here. So it's the natural log absolute value of v minus natural log absolute value of v plus 1. We're going to evaluate that from 1 to b. So the limit as b goes to infinity. It's the natural log of absolute value of b, but I'm going to get rid of the absolute values because b is a positive number, minus the natural log absolute value of b plus 1, but I'm going to get rid of the absolute values because b is a positive number, minus 1 comes in, so the natural log of 1 minus the natural log of 2. Yeah, I'm just going to clean this up a little bit. We have the limit as b goes to infinity. ln b minus ln of b plus 1 minus the natural log of 1 is 0. So it's 0 minus ln 2. So minus negative ln 2, so that's plus ln 2. All right, so let's make a progress check. We're trying to find a limit. I know this. The limit as b goes to infinity of ln 2 is ln 2. We know that. This is infinity. This is infinity. But here's a problem. We have the limit as b goes to infinity of infinity minus infinity. That's an indeterminate form. We don't know how to handle that. So let me erase that over there and show you what I think we're going to need to do. So we have an infinity minus infinity. So just for those natural log things that are giving us problems, I think we need to use a property of logarithms. Property of logarithms that says subtraction can be rewritten as division. So the natural log of b over b plus 1. So, let me just kind of pull it right here. So I'm rewriting that as the natural log of b over b plus 1. And, oh, don't forget, I still have that natural log of 2. But I still have a problem here. Now I have infinity over infinity. Before I start to rush off and say, hey, I can use L'Hopital's rule again, I think I can get by with a little bit of algebra here. I think if I come in here, look at the fraction, b over b plus 1. I can divide everything in the numerator by b, and I can divide everything in the denominator by b. b divided by b is 1. b divided by b is 1. 1 divided by b is 1 over b. So I think that now helps me tremendously. I rewrite this as 1 over 1 plus 1 over b, because now I can do it. When I look at the limit as b goes to infinity of this first term here, well, as b goes to infinity, 1 over b would be going to 0. 1 plus 0, 1 plus 0 is 1. 1 divided by 1 is 1. The natural log of 1 is 0. the limit as b goes to infinity of natural log 2, that's a constant. The limit of a constant is that constant. So I get the value of the improper integral to be natural log 2, which tells me that this improper integral converges. It converges and it has a value of natural log 2. All right, let's head back to the slides and see what we're going to attack next. All right, in that last example, besides dealing with an improper integral, well, we saw we needed to remember the technique of integration by parts, and then in I asked you to do number 31, and in doing 31, partial fraction decomposition came about. Also, in that example we did, in trying to find the limit, I thought it was pretty cool. We had to review an old topic from Calculus 1, L'Hopital's rule, and I'm sure you're going to see that in the immediate future. Next up is, well, another example. We're going to integrate from negative infinity to infinity 1 over 1 plus x squared dx. So here I go, off to the chalkboard to work through this example. All right, in this example, we're going to integrate from negative infinity to infinity 1 over 1 plus x squared dx. So we're integrating over the entire real number line. This is an improper integral, no doubt about it. And the first thing we have to do is we have to find a convenient value for x to break up the integration so we can write it as two separate improper integrals. I think a convenient value for x would be 0. So let's start by just rewriting this as negative infinity to 0 of 1 over 1 plus x squared dx plus the integral 0 to infinity 1 over 1 plus x squared dx. This improper integral, I know I can't do it, but I can rewrite it as the limit as a goes to negative infinity, the integral from a to 0, 1 over 1 plus x squared dx. And this one I rewrite as the limit as b goes to infinity, the integral 0 to b, 1 over 1 plus x squared dx. Doesn't look too bad because we know the antiderivative of 1 over 1 plus x squared. We know that antiderivative is inverse tangent. So I have the limit as a goes to negative infinity, inverse tangent of x evaluated from a to 0. And here we have the limit as b goes to infinity, inverse tangent of x evaluated from 0 to b. And just pulling that up here, and using the fundamental theorem of calculus, we have the limit as a goes to negative infinity, inverse tangent of 0 minus inverse tangent of a plus the limit as b goes to infinity. So I use the fundamental theorem of calculus on this one. It's inverse tangent of b minus the inverse tangent of 0. All right, we can do a little cleaning up here. We know, we know inverse tangent of 0 is 0. So let me go ahead and take care of that. Likewise, we know inverse tangent of 0 is 0. So we need to find the limit as a goes to negative infinity, the opposite of inverse tangent a, and the limit as b goes to infinity, inverse tangent of b. In case I haven't mentioned it, knowing the graph of inverse tangent can help quite a bit in doing limits this is the graph. So as you head off to negative infinity, this limit is negative pi over 2. So you have the opposite of negative pi over 2. As you go to infinity, this limit is pi over 2. So the opposite of negative pi over 2 plus pi over 2, that gives you 2 pi over 2, or pi. So this improper integral, it converges, and it has a value of pi. All right, let's head back to the screen, or the slides right now. We're going to take a quick look at how to handle the other type of an improper integral. And the other type was when you have an infinite discontinuity. So let's go check that out. All right, so next up on our list is, how do we attack the infinite discontinuities? For example, consider the integral from negative 1 to 1, 1 over x squared dx. If we happen to proceed completely oblivious to the fact that there is an infinite discontinuity at x equals 0 in the interval negative 1 to 1, well, here's what we'd end up getting. We would evaluate that from negative 1 to 1, 1 over x squared. We would rewrite that as x to the negative second. We would get the antiderivative to be negative 1 over x. From negative 1 to 1, we'd crank that through the fundamental theorem of calculus, and we'd get negative 2. That's if we proceed completely oblivious that on the interval negative 1 to 1, there's an infinite discontinuity at x equals 0. But a quick look at the graph should tell us that that answer, negative 2, is not reasonable. I mean, here's the graph of the function 1 over x squared. I mean, look at the interval negative 1 to 1. Look at all of that area that is above the x-axis. Doesn't seem reasonable that the result would be negative 2. So we can't proceed oblivious to it. We have to figure out, well, how do we attack the fact that there's an infinite discontinuity for this problem at x equals 0? So I'm going to look at this, like 3 separate cases. So to handle integrals that have infinite discontinuities at endpoints of the interval or interior points of the interval, we're going to do the following. So I'm going to break it into 3 cases. First, if the function is continuous on the interval a to b, notice the square bracket around a, parenthesis around b, and there's an infinite discontinuity at b. Some people call that a right endpoint discontinuity because the discontinuity is at the right endpoint of the interval. To integrate from a to b f of x dx, we rewrite that as doing the limit as c approaches b from the left, the integral a to c f of x dx. If the function is continuous on the interval a to b, notice parenthesis around the a, closed bracket around the b. That's saying our infinite discontinuity is at a. Some people call this the left endpoint discontinuity because it's occurring at the left endpoint of an interval. Well, then the integral from a to b f of x dx would be rewritten as the limit as c approaches a from the right side of a. Integral c to b f of x dx. And if the function is continuous on a to b, the closed interval a to b, except for some c in a to b, and f has an infinite discontinuity at c, then we take the integral from a to b f of x dx and we split it at that value where there is the infinite discontinuity, and we use the interval addition property to rewrite it as the integral from a to c f of x dx plus the integral c to b f of x dx. And then we can handle either of those integrals on the right via number 1 and number 2. So let's make sense out of this. And, usually it will help with an example and how if you just think about it and do a quick sketch of something, it's kind of self-evident how to attack the problem. So this example, in part A, we're going to evaluate the integral from 0 to 1, 1 over the 4th root of x dx. B, we're going to integrate from 0 to 2, 1 over x to the 4th dx. And then in C, we're going to integrate from negative 1 to 2, 1 over x to the 4th dx. So get this written in your notes. I'm going to head off to the chalkboard to do it. And you'll see when I do A and B, if I do a quick sketch of a number line, it tells me exactly what the limit statement should be. But here I go to the chalkboard to work through it. All right, this example, there were 3 improper integrals that we're going to evaluate. In A, it's the integral from 0 to 1, 1 over the 4th root of x dx. B, 0 to 2, 1 over x to the 4th dx. And then in C, it's the integral negative 1 to 2, 1 over x to the 4th dx. So let's start off by doing A. All right, so the first thing I note, we do have a problem here. It's an improper integral because the function, the integrand, 1 over the 4th root of x, it's not defined at x equals 0. That's where our infinite discontinuity is. In fact, if I know where my infinite discontinuity is, if I just make a number line, I'm integrating from 0 to 1, that's where the infinite discontinuity is. So I'm on this interval here. I can integrate from any number greater than 0 to 1. So I can integrate from C to 1. I can integrate from C to 1 and then let C approach 0. And that tells me exactly how to rewrite this problem. I integrate from C to 1. Out front I put the limit as C approaches 0 from the right. What is it I'm integrating? Well, 1 over the 4th root of x, which I would rewrite as 1 over x to the 1/4, which is x to the negative 1/4. So I get my antiderivative. Antiderivative is 4/3 x to the 3/4. Crank it through the fundamental theorem of calculus. So that gives me, oh, that's not too bad. That's a 4/3 minus, put c in, so I get 4/3 c to the 3/4. The limit as c goes to 0 from the right side of 0, of 4/3. Well, that's just 4/3. The limit as c goes to 0 from the right side of 0, of 4/3 c to the 3/4. I can find that by direct substitution. I can directly substitute 0 in for c. 0 to the 3/4 is 0. 4/3 times 0 is 0. 4/3 minus 0, 4/3. So part A, this improper integral has a value of 4/3. So now part B, so let me erase this so I can do part B. Part B, we're integrating from 0 to 2, 1 over x to the 4th dx. Same thing, I have a problem at 0. That's where my infinite discontinuity is. So, when I look at the real number line, 0 to 2, I can integrate from c to 2, and then I'll let c approach 0 from the right side of 0. So I rewrite this as the limit as c approaches 0 from the right side of 0, integrate from c to 2, and I'd rewrite 1 over x to the 4th as x to the negative 4th. Get an antiderivative. See, antiderivative, I'd add 1 to the exponent. The multiplier out front is the reciprocal. Evaluate that from c to 2. And I'll put in one more step. This just kind of helps me. Make that exponent positive again, so I get 1 over 3x cubed. Evaluate that from c to 2. All right, so fundamental theorem of calculus. Two comes in first. 2 cubed is 8. 3 times 8, 24. So I have a negative 1 over 24 minus negative, so that'll make that a plus. 1 over 3c cubed. Okay, so I know the limit as c goes to infinity of negative 1/24 is negative 1/24. The limit as c goes to 0 from the right, so the limit as c goes to 0 from the right side of 0 of negative 1/24 is negative 1/24. The limit as c goes to 0 from the right side of 0 of 1 over 3c cubed. Well, if I think about substitution, I think about putting 0 in for c, this denominator becomes 0. When you take a number, a non-zero number, and divide it by 0, when you divide by something that's really, really close to 0, you're getting incredibly large. So the limit as c goes to 0 from the right side of 0 of 1 over 3c cubed, that limit is infinity. Negative 1/24 plus infinity, we get infinity. So that improper integral diverges. Part C. I want you to pause the video and I want you to do part C. After you've done part C, restart the video. I'll be here at the board working through it. All right, folks, I asked you to do part C. I asked you to integrate from negative 1 to 2, 1 over x to the 4th dx. Our infinite discontinuity is at 0. This is an interior point problem. 0 is inside the interval negative 1 to 2. Because that's where the problem is, that's where we're going to break up the integration and write down our two separate integrals. So we rewrite this problem as integrating from negative 1 to 0, 1 over x to the 4th dx, plus integrating from 0 to 2, 1 over x to the 4th dx. And at this point, I think I'm done. Because in part B, we integrated from 0 to 2, 1 over x to the 4th dx, and we saw that this integral diverges. So remember, if either one of these integrals diverge, and we know this one here diverges, that tells us the original diverges. And we're done. That's it. Nothing more to do for part C. So hopefully you got that one pretty quickly. Alright, so knowing what's coming up in the next chapter, improper integrals are really important, especially when we're integrating on an infinite interval, like integrating from 1 to infinity. These improper integrals that have an infinite discontinuity, they're neat, they're nice, I like looking at them, but they're not as important as the first ones we did. But before we finish this section, I want to go back to the slides and talk about something that is really, really important. It's setting us up for the next chapter. So let's head back to the slides and see what I'm talking about. All right, that example wasn't too bad. And, as I mentioned, That was just looking at when we have infinite discontinuities, how to handle those improper integrals. The improper integrals that are going to be of the greatest importance to us, especially in the next chapters when we start to look at infinite series, are going to be the improper integrals where the interval is not finite. Say we're looking at the interval 1 to infinity. With that said, I want to conclude this section with a theorem. This theorem, it's going to lay the foundation for a special family of infinite series that you will soon see called P-series. You're going to see this when we get started in the next chapter, the series called P-series. But here's the theorem. This theorem pertains to improper integrals. The integral from 1 to infinity of 1 over x to the p dx, that improper integral is equal to 1 over p minus 1 if p is greater than 1. And that improper integral diverges if p is less than or equal to 1. So if that exponent, p, if it is greater than 1, the improper integral converges, and we know its value is going to be 1 over p minus 1. So that's it for this section, folks. At this time, you can, you can head off, do all the exercises in the section. Thanks for watching.